Okay, we're going to learn about the fundamental theorem of calculus. Sometimes this is called the first fundamental theorem of calc because there is a second fundamental theorem later on. And it really is just the definition of integration. It's something I've taught you already, but now it's formalized. All right, so basically what we have is we have capital F is an antiderivative of lowercase f. So in other words, the way I see this is capital F is the parent function, while lowercase f is the child. And as juvenile as that might sound in my example, I have seen textbooks that do use parent function as official terminology, so it is mathematical. So if you think about it, over here on the left-hand side, we're integrating the child. That's what it says. And you would think that if you integrate the child, you go up by a power. That's almost like going up by a generation, and you end up with capital F, or the parent. So that makes sense. In between them is the minus, and that's what Gottfried Leibniz and Isaac Newton discovered. And then, as I taught you already, you put the upper limit of integration in first, minus, and you put in the lower limit. So this is really just explaining how to do a definite integral that has a name. It's the first fundamental theorem of calc, or simply the fundamental theorem. FTC, sometimes it'll be abbreviated as. All right, very cool. We're going to use the fundamental theorem as we move ahead with our examples. This will probably be more or less a review for you, at least at first, and then we will jazz it up a bit. So let's do it. Okay, number one. First off, we want to integrate. Up by a power, divide by the new power. So 3x squared will become x to the third. Then we have plus 2x squared minus 6x. Now I have to tell you, most, if not just about all teachers, just draw a straight line here and put the 2 and the 5. That's pretty much standard notation. But my math teacher in calc put brackets, and he put brackets around both sides. And there's something about, when you first see something that sticks with you, and I can't get this out of my mind. So I don't know if I feel like I'm protecting the function. So I put them on both sides, but I have to tell you, that's atypical. Usually you don't see teachers do that. So, all right, so first fundamental theorem, it says put the 5 in first. 5 times 5 times 5, that'll be 125. 5 squared is 25 times that 2, that's going to be plus 50. Minus 6 times 5, so that's minus 30. Okay, a subtraction is always in the middle. And then in goes the lower limit, in this case the 2. 2 to the third is 8. Plus 2 times 2 times 2, that's another 8. Minus 12. And then we just have to figure out what this is. It's going to come out to a number. That's what the directions evaluate mean. It means you're going to get a cool number answer, numeric. That's going to be 145 over here. Minus 4. And that's 141. Easy enough. Let's get a little bit more difficult. In number 2, I have a fraction. And really, that x to the 3 halves that's down there, you could split this up into 3 different things. You could think of it as being this, which would be 6. But remember from Algebra 1, you subtract the powers when you divide. 7 halves minus 3 halves is 4 halves, which is just 2. So this is going to be 6x squared. Employing the same strategy, we have minus 2. And 5 halves minus 3 halves is 2 halves. That's just 1, so x to the first. And then finally, plus 1 over x to the 3 halves is simply x to the negative 3 halves, dx. All right, now let's integrate. Up by a power, divide by the new power. So 6x squared will become 2x to the third. Then we're going to have minus x squared. Hopefully you can follow this. It's going to be minus 2x to the negative 1/2 You can always double check me on that if you don't see where I got that from. And the limits of integration are still on there. We're going to integrate from 1 to 4. So the 4 is going to jump in first. And this thing I'm doing in blue has a name, and it's called the first fundamental theorem, or just fundamental theorem of calc. All right, 2 times 4 times 4 times 4, that's going to be 128. Minus 4 squared, so minus 16. Minus, oh boy, okay, negative 2 over rad 4. It's just going to be minus 1. Okay, so that's the 4 going in. Now we're going to subtract, and we're going to repeat the process with the 1. Of course, 1 to the third, 1 to the second, 1 to the negative half, those are all just 1s. So really this ends up being 2 minus 1 minus 2. Putting this together will yield 111 minus negative 1, which will be 112. Final answer. All right, let's kick it up another notch, shall we? Oh my gosh, this looks crazy. Full of trig. This is where if you were in pre-calc, or if you did a really good job in Algebra 2 during the section where you learned the pre-calc, and you're good with the golden sheet, this is really gonna help you out. I see sine squared plus cosine squared up top, and I realize that's a 1. And then I see 1 plus tangent squared, and I'm like, yeah, that's secant squared. And then I see that I can cancel a secant out. I'll get rid of the squared. And I have secant over cotangent. Of course, I'm not a big fan of cotangent. Really, that's not even a cotangent. It's 1 over cotangent, which is really just a tangent. So really, before I start this problem, it ends up being secant of x times tangent of x, dx. At this point, you're like, wait a second. Secant tangent, that's somebody's derivative. That's the derivative of secant. We're going backwards. We're taking an antiderivative, so we're back to secant of x. Oh my gosh, this is cool. And now we just have to plug in the upper and lower limits of integration. Here we go. Secant of pi over 3, secant of 60. Well, the cosine of 60 is 1/2. That means the secant of 60 must be 2. All right, minus. In goes the 0. The cosine of 0 is 1. The secant's the reciprocal. It's still 1. And the answer, 2 minus 1, is 1. See, even though that problem looked crazy when we started, my knowledge of the golden sheet, I used the golden sheet 3 different times on this, and I used the trig derivative going backwards. So things broke down in a hurry. All right. Okay, I want to integrate this absolute value function from -10 to +4. I think I'm going to graph it first, even though this is not really required. I think it's going to help me out. So let's see, 1/2 x plus 3. 3. The positive side of it's going to be easy. I just go up 1 over 2. It would be a straight line. This straight line would keep going. But being absolute value, as soon as it hits the x-axis, it's got to bounce. So instead of being down here, as you figure it would be, it's going to be up above the x-axis. And it's going to bounce that way. All right, so the integral from -10 to 4 would end up being the same thing as the combined areas of those two yellow triangles. Well, heck, I have done areas of triangles since I was a young kid. That's 1/2 base times height. I don't need calculus for that. I'm taking the easy way, and why wouldn't I? This first triangle here, circled in red, is going to be 1/2. Let's see, base is 4, height is 2. That's half of 8, so that's a 4. The triangle over here that I'm circling in green has a base of 10 and a height of 1, 2, 3, 4, 5. 10 times 5 is 50. Half of that's 25. Add those two together, 4 plus 25. The answer is 29 square units. That's the area. And so that's the integral, 29. Notice that the problem said evaluate. It didn't say find the area. So if those yellow regions had been below the x-axis, it could be negative 29 for the answer. I just want to point that out. Even though integrals represent areas under curves, they're not the same thing. Areas can't go negative, integrals can. All right, now, of course, I kind of was a little sloppy on that problem. I cheated and used like elementary school math instead of calculus. Hey, yeah, that's cool. I think that was brilliant. But there is a technical definition of absolute value, and I'd be remiss not to show it to you, so we're going to go there. So the technical definition of absolute value is this. The absolute value of x is just x, if you already have positive numbers. I mean, you think about it. Let's say you had a number like 17 that was already bigger than 0. If you put an absolute value on it, a computer is taught, you know what, just take the bars off. Dude, it's just 17. Okay, but if it's negative 17, and there's bars on it, and the number inside is less than 0, which negative 17 is, a computer is taught, okay, take the bars off, but the thing inside, which is the x, which is the negative 17, go ahead and throw an additional negative on it, which will turn it positive. So that's the technical definition, and we can use that to integrate with. And I'm going to show that right now. You can break the original problem up into two separate parts. From negative 6 to positive 4, you can see that the absolute value being taken off doesn't affect anything. The curve y equals 1/2 x plus 3, if you were to use slope-intercept form, would just be this. However, the absolute value bounces, and so this red portion of it, what you have to do is take the formula, take the bars off, but change both of the signs, and that's what I did over here. You can see it right there. And interestingly enough, if this line were to keep going, it would cross at negative 3. It has a slope of negative 1/2, so it kind of makes sense that you're taking the integral from negative 10 to 6 of that. That would color this in. And then the other part, going from negative 6 to 4, using the other equation, would color this part in. And so working that out would also give you 29. In fact, you get the same numbers that you had before. This would be the 4, and this green part would come out to be the 25, and it would work. So again, if they don't say anything to me, or if this is multiple choice, I'm using triangles. If your teacher or professor says you must show the technical definition, then you have to split it into a piecewise function and chop the area up into two different parts. Okay. Speaking of area, let's find the area of the region bounded by the graphs. Now this does, for the very first time, say area. Find the area. So if you get anything that's negative, we are going to change the sign. It doesn't say find the integral or the antiderivative or evaluate or something like that. It's just find the area. All right, y equals 0. Y equals 0 is the x-axis. So that's one boundary. The other boundary is a cubic. I know that that green x to the third minus 4x graph, I know it goes through 0, 0. I also know that it goes through 2, 0, because if you plug a 2 in, you get 8 minus 8. It also goes through negative 2, 0. Just for fun, if you plug a 1 in, I just want to get a good looking graph. You get 1 minus 4, that's negative 3. This is an odd function, so it'll have origin symmetry. All right, that's good enough. Here's my graph. I just like to take my time and be accurate, because then I can estimate. Some people will tell me that the answer is 0, and I'm like, I see yellow though. There's no way the answer can be 0. There's definitely area between green and red. Now realize that it's symmetrical, and the top yellow will cancel the bottom yellow out, but it doesn't say evaluate or integrate. It's just find the area. So what I'm going to do is I'm just going to take half of it. I'm going to take the integral between, let's say, 0 and 2. And there's going to be a couple things that are wrong with this. First of all, it's only going to give me this. It's going to report a negative answer because it's below the x-axis, so I'll throw a negative sign in front to make it a double negative and kind of trick it into giving me a positive answer. But I also need to include this, but I don't want to integrate because it's going to cancel. So I'll just use symmetry and I'll double my answer. So I'm going to put a 2 out front, multiply by 2, and that way this will give me the correct answer. Okay, here it goes. Let's integrate. X to the third becomes 1/4 x to the fourth. The minus 4x becomes minus 2x squared. We're integrating from 0 to 2, and there's still a negative 2 in front that we can't forget about. All right, we're going to use first fundamental theorem of calculus. In goes the 2. 2 to the fourth is 16. 1/4 of that is a 4. Minus 2 times 2 times 2, that's 8. Okay, subtraction in the middle. Obviously, plugging the 0 in is going to be a 0 minus 0. I'm not sure why I keep writing that, but I guess it's just going to happen. Okay, that's gone. So the answer is going to come out negative 2 times negative 4. That's positive 8. And that makes complete sense because if you start counting blocks, 1, almost 2, it looks like you could probably get 4 blocks out of this and 4 blocks out of this. So this is going to come out to 4. This will come out to negative 4. And 4 minus negative 4 plus plus is also 8. So yeah, it works. Okay, same sort of setup. We still have our y equals 0, which is still the x-axis, which will serve as a boundary. And then the other graph in green is again a cubic. Just to save time, I did a quick, fairly accurate sketch of it. And now we want to find the area between those two, between the green and the red. Unlike number 5, it's not perfectly symmetrical. You can tell that the region that's above the x-axis has got a bigger area than the region below. So we can't just double the answer. We're going to have to do a little bit more work on this one. In order to get the overall area, we'll start with the bluish region first, from negative 3 to 0. And again, it'll just be that equation. To get the yellow region, we're going to integrate from 0 to 2 because that's where that crosses the x-axis. But the problem is, since the yellow region is below the axis, it's going to come out as a negative answer. So I'll put another negative in front to make a double negative and kind of trick calculus into doing what I want. Rather than writing this again, I'm just going to write same. Maybe a bit lazy, but I think it's brilliant. dx. That way I don't have to integrate twice. It's going to be the same integral both times as well. In fact, the integral is going to be 1/4 x to the fourth plus 1/3 x cubed minus 3x squared. And that's the same both times. And then we just use our calculator to plug some of this stuff in. I don't really need a calculator to plug a 0 in. I know that's going to be 0. And in fact, on the back end, it's also going to be a 0 here. Plugging the negative 3 into all 3 parts will give me negative 63/4. And plugging the 2 in will give me negative 16/3. Both of these will turn positive, which they should because we're looking for an area. And so I'm guaranteed to have it work out the right way. 63/4 plus 16/3, if you get a common denominator, comes out to 253/12 or 21.08333 repeating units. That's 21 and 1/12. That's it for number 6. Okay, number 7 and 8 will be the last two for day number 1 of this section. We want to integrate from negative 1 to 1 in both cases. I've already graphed them so you can kind of see them. This is where pre-calc really is an advantage. If you were to look at this function, that function is odd. And this second function right here, that's even. So we can use some nice shortcuts here. First of all, the odd function, whatever this turns out to be, this is going to be the exact same area, but it's below the x-axis. It doesn't say find the area, it says evaluate, which means they're going to cancel each other out. And doing no work whatsoever, I get the correct answer of 0 here. Now, if it said find the area between the curve, it would not, the curves in the x-axis, it would not be 0. I'd actually have to do some math. But no. Now, the even function, again, is a little easier by the fact that it's even rather than if it had been a neither. Here, instead of going from -1 to 1, I can just go from 0 to 1. Here's 1, by the way. So I can find this area only instead of needing to go from -1 to 1. So I'm just going to double my answer. So this is going to be 2 times, and I can put a 0 in the lower limit. That just makes it easier. Because as you guys have seen, plugging in a 0 is the best number to plug in ever because you don't have to do any work. So why not? All right, I'm just going to rewrite the original problem. And now I'm going to use calc. The 2 is still out there. The 5x to the 4th integrates up to x to the 5th. The 9x squared becomes minus 3x to the 3rd. And what could be easier than plugging in 1s and 0s? Gotta love it. 2 still in front. The 1 goes in and makes 1 minus 3, which is -2. I'm not even going to bother plugging the 0 in, it's 0. You get 2 times -2, that's -4. And -4 is the answer. Don't take the negative off of it. It doesn't say what's the area. It says evaluate. And all that green stuff is below the x-axis, so the answer is -4. It's a pair of -2's. And if you think about it, did you fill in a total of 4 blocks coloring it in green? Probably. It looks pretty close. That's because it's right. All right, so that's it for day number 1.